right then, this is the video I promised you on the Trig worksheet you sent. That worksheet is mostly grade 11 revision. So it's quite a lot of work. I'm trying to make this video as short as possible because the size of these things is insane. Okay, so let's get right into it. So we have question 1. Okay. That 5. All right. So question 1. Let me bring up the worksheet here on my phone so I can see it as well. All right. If 5 tan theta minus 3 is equal to 0. Okay, so they give us those conditions for 5 tan theta minus 3. So for the sake of making this video short, I'm not going to be writing the questions on the screen. You're going to just check them on your phone or on your laptop so you can see what's going on. And they set the conditions as 180 degrees, theta's between these two angles. All right. So in these cases, the most important thing is cost. All right, where cos is positive in this quadrant, all of them are positive in that quadrant. Sine is positive here, tan is positive here. And the origins of cost, just in case you do not know, is, let's say I have an angle here, theta, and let's give it hypothetical values. Let's say this is 3, this is 4, this is 5, right? If, let's see, sine theta, cos theta, and tan theta. All right, here sine theta is 3 over 5, which is positive, and then cos theta is 4 over 5, and then here tan is 3 over 4. All right, so this is Q1, so that's the first quadrant. So let's go to the second quadrant. In the second quadrant, sine theta is a triangle that looks like, in the second quadrant you have a triangle that looks like that. You have theta there, you have 3, this becomes minus 4, and this is 5. All right, and that is 5. So now sine theta is still 3 over 5, which is still positive. Cos theta is now negative 4 over 5, which is now making it negative. And then tan is now 3 over negative 4, which makes it negative. So it's these shifts where these triangles are in each quadrant, and these values for 3, 4, and 5 are changing in signs with each quadrant specifically. That gives rise to this cost diagram. So if we draw a quick little diagram for our, if we have our equation, we have 5 tan theta minus 3. The goal here is to isolate our trig ratio, which is tan theta, right? So we're gonna have tan theta is equal to 3 over 5. So I moved over the 3, changed the sign, and then divided by 5 on both sides. So if tan theta is equal to 3 over 5, tan theta can be said to be in the first quadrant. How do we know it's in the first quadrant? Because I've forgotten there. All right, so now we need to figure out which quadrant tan theta is in. So tan is positive, and the two quadrants that tan can be positive in is this one and that one there. So which one of the two is it? We look at our condition here. We know that theta is between 180 and 360. So 180 is here and 360 is here. So it can only be this quadrant here. So there, we're going to write down our theta. We know tan is equal to 3 over 5, which means this is our tan. So now let's find our hypotenuse. We're going to say r squared is equals to 5 squared plus 3 squared, which gives us 25 plus 9, which gives us 34, and that's r squared. So r is equal to the square root 34 right there. Okay, so now we have a value. We have a triangle for our theta value, right? And the question tells us to determine this right here, 2 sine theta minus cos theta, and that gives us, so what's our sine theta, right? We're going to say 2 times whatever our sine theta is. Sine theta is 3 divided by root 34, so we're going to have 3 over root 34 minus cos theta, which is 5 over root 34. Okay, so we solve this question. We're going to have 6 over square root of 34 minus 5 over root 34. Adding or subtracting fractions, that gives us 6 minus 5, which is 1. Oh, yeah, 1 over square root of 34. And there is our answer. All right. So, moving on, we have let me see. We have 1.2. This video is going to be pretty long, especially once we get to the identities. So I think what I'll do is, let me just, that's the basic concept that we use. Let me do 1.2 because 1.2 is quite a significant one. So 1.2 gives us this. I'm going to skip 1.3, but I'll do 1.2 now. Gives us 8 sine beta plus 7 is equal to 0. And the quadrant condition they give us is beta is bigger than 0. So let's quickly manipulate our equation. Say therefore sine beta is equals to negative 7 divided by 8. So now we need to figure out what quadrant our triangle's in. We have a negative sign, so it's either one of this one or these ones. And they say, is it cos beta there? Sorry. So this is cos beta is positive. So we know cos is positive in this quadrant. So sine is negative here and cos is positive here. So it's definitely this fourth quadrant here. We have beta, right? Sine beta. And I want you to see why this makes sense right here. In this quadrant, your opposite is a negative 7. And obviously your hypotenuse would be positive. So that makes sense as to why sine is negative in the fourth quadrant. So using Pythagoras, let's figure out our adjacent value here. I'm going to say x squared. I'm using x for the adjacent. If I was looking for the positive, I'd use y. So we say x squared is equal to r squared minus y squared, which gives us 8 squared minus negative 7 squared, which is 64 minus 49. And that I've got written down here is 15. That's equal to 15. All right, yes, that's a very, very crazy 5 right there. that is equal to 15. That's x squared. So x is equal to the square root of 15. Okay, so now we can solve our question. They tell us we need to determine tan squared beta, and that is equal to, we're going to have our tan squared, of course. And so what's our tan? We have beta here, we have the positive square root of 15 here, opposite negative 7 over the square root of 15, which gives us 49 over 15. I'm not sure if that can be simplified. Let me check my calculator. I doubt it though. Over 15 is, yeah, that's your final answer there. All right, so moving on swiftly, we have question 2. Okay. All right, so 2.1. Question 2 is very similar. All of them are very, very similar. And what's important in question 2 is you need to understand reduction. You need to understand reduction. And reduction takes two forms, right? You have reductions on from the x-axis, or you have reductions from the y-axis. What does this mean? So if I'm reducing from this axis, my x-axis, I'm gonna use my 180 line or my 360 line as my reference. So this quadrant, all of them, we don't really check this quadrant. This is where the angles are normal and simple. But here we'll have a 180 minus x, and it's minus x because any angle in here is going to be smaller than 180, right? So all right, and then here we'll have 180 plus x. Here we'll have 360 minus x, and then on this iteration we're gonna use the 90-degree line and the 270-degree line. Most often you're going to see the 91 and not really the 271. So here we'll have the 90 plus x, and here we'll have 90 minus x. All right, and then here we have 270 minus x, and we have 270 plus x. All right, so let me just separate these here like that and see what are the quirks of this thing, right? Hold on, let me just bring out my notes on these reductions so I make sure I've got everything. Okay. Okay, so there isn't really much to say about these ones. These are the ones you're going to encounter most often. These ones here you will encounter. This is an O. The most. And you use these ones only when you must. Okay, so but these ones are the ones that have a lot of really special quirks. Your 90-degree reductions here. All right, what are their quirks? Well, 90-degree reductions work with complementary angles. So complementary angles are angles that add up to 90 degrees if you're thinking back to your geometry. So if I have 20 here, then this would definitely be 70 degrees, and 20 plus 70 is equals to 90. And there's some very special properties about complementary angles that we'll explore just now. So let's quickly speak about what type, I'm going to put that in a different color, what type of situations we encounter when we see this. You'll notice that these ones, also, let me just put a note here. These complementary reductions, let's call them that, complementary reductions, only deal with sine and, let me not put a plus there, and cos. All right, that you will never have a 90 reduction that involves tan. All right. Okay. So what are these reductions and how do they work? All right. Let's see. So with these ones, you get four instances. For example, if I give you a sine of 90 degrees minus x, all right, that is equals to cos cos x. Just a quick reflection on why this is the case. Let's look at a triangle here, right? Let's give these angles names. We have 20 there, we have 70 there, right? And this is 90. If you add all of these, they'll equal to 180, right? Let's say this is 1, this is 2, this is 3, right? So we'll have sine 20, right, degrees. That sine 20, oof, this is very ugly. Okay, sine 20 degrees will equal 1 over 2. Now let's look at cos of the complementary angle, which is 70 degrees. What's cos of 70? That's adjacent over hypotenuse, and that's equals to a half. So these are the same. All right, so that's why we have these identities, and we teach them in this way because it's actually quicker in your work process to just memorize this, and for you to know, it's good to know where it comes from, but for you to memorize that if I see a sine 90 minus x, then I know it's cos x. If I see a cos 90 minus x, and that will equal sine x. All right, if I see a sine 90 plus x, that will equal sine 90 plus x, that will equal cos x. So all of these are normal. Like you get your ratio and you just switch it over to the opposite one, or to the other one, which is cos, right? And then the last one, the fourth one, is the weird one. If I have cos of 90 plus x, that will equal negative sine x. So this one is the one that deviates because now you have a negative there. All right, and I could show it to you graphically where this works, and this is what you always get. But for the sake of time, let's go. We can move on. Let me just make sure I haven't left anything in terms of the 180 reductions. Okay, yeah, we can go on. So there are some special cases. There are indeed some special cases. So if I give you this question here, let me put it in a, bring my red out here. All right, if I was given this question here, let's say EG 1, it says I need to reduce sine sine of x minus 90 degrees. Now already you can tell that this is very odd because now we have an x minus the 90. So personally, initially, I solved this incorrectly. I tried to add 360 to this, which wasn't the correct way to do it. The more mathematically sound, so I tried to do this. I tried to do sine x minus 90 degrees plus 360 plus 360 degrees, which is obviously what you do, because if I have an angle here, and let's say this is like, if I add 360 to it, I'll bring it back, but in a quadrant I can work with, right? So I thought that would work. I thought that would work, but it gave me an incorrect answer. I thought it would go at sine, then I'd end up with sine. Um, that's 270 plus x, right? And then I tried to work it out in this way. So it turns out this wasn't correct. This wasn't the correct way to deal with this. So what is the correct way? The mathematically sound way is to remove an x. So this is equal to sine bracket. I'm going to remove a negative. I'm going to take out a negative from this bracket such that I'll have a positive 90 there and a negative x there. So mathematically, what does this mean? For sine, it means you take out a negative there, and it gives you 90 minus x, which I can then solve, and that gives me negative cos x. All right. So what about cos? How does this work for cos? We'll go to example number 2. All right. Example number 2 is cos, cos of 90, or rather x minus 90, cos x minus 90. All right. Okay. We have cos of x minus 90. What's going on here? So, true to form, let's try and remove a negative. Negative. So we'll have 90 minus x. And so here's where cos differs from sine. This negative does not change the cos. We'll have 90 degrees minus x, and that is sine of x. All right. Let me see if I can show you these quick reasons as to why. Do I have them here? All right. So here, if for cos quickly, cos of minus x is what? Graphically, that means this. Cos, if x is here, then its negative angle will be there. So this is minus x, right? And so cos is the adjacent, which is positive there, and that's positive. So the sign of cos is still positive, even if it's minus x, and that's why the sign doesn't change for this one. All right. So essentially, cos x is equal to cos x, but it's different for sine x. For sine x, so we have sine of negative x. That will give you a negative sine x, because negative x is there, right? I'm just going to put a negative there. It's not conventional for us to do that. Essentially, when you give a negative to an exponent, instead of going anti-clockwise, which is positive, we go clockwise, which is negative. So this is the positive direction, this is the negative direction. All right. So sine of negative x is opposite over hypotenuse. Here the opposite is on the negative side, so that's a negative, and obviously that's a positive. So the sign changes. So that's negative x. Sine of negative x is negative sine x. All right, so those are the two types of reduction that you come to. All right, quick examples. I'm not sure if you're gonna need examples, but I just needed to do that explanation fast, and then we can get back to our question. So what does our question say? Our question gives us that okay, 2.1, it says if sine 20 degrees is equal to p, right? Determine the following in terms of p. So here we have 2.1.1. So here, take note of what they're telling us. Sine 20 is equal to p over 1. And we can construct a triangle out of this. In trig, always try and construct a triangle. So here we have 20 degrees. Sine of it, opposite of our hypotenuse, is equal to p over 1. So let's use Pythagoras to find our adjacent value, right? So here we're going to say x squared is equal to 1 squared minus p squared, which gives us 1 minus p squared, of course. If then that's x squared, we're going to then root both sides, and that gives us the root of 1 minus p squared. So this value here is 1 minus p squared. All right, if this is the case, so 2.1.1 wants us to find sine of 160 degrees. Okay, so how do we find this? It's 160. I don't really know what this is, so let's try and reduce it. 160 is in the second quadrant, right? So I can do this. Sine of 180 degrees minus 20 degrees, and that gives me sine 20. So this is that normal reduction we were doing here, the one you most encounter. Okay, so if that's the case, with our normal reduction there, I would then come in and say sine 20 is a value I know. Sine 20 is p over 1, which is p. All right, so that's how you deal with this question. Let me just look at my thing and see if there is like a weird one that stands out with these complementary ones. Okay, let's look. Yeah, there's question 2.1.2 is complementary. So let's check that out. All right, here we have 2.1.2. All right, what does 2.1.2 tell us? It says find cos 70 degrees. So immediately when I see 70, your mind should be like ringing bells, because I know 70 is complementary to 20. So I know that cos 70 is actually equals to sine 20, which is what we know, and we know that's p. All right. Okay, so that's these ones. Just be really careful that when you're reducing, you have the option of using the 180 360 reductions, or you can use the 90 to 70 reductions. Most often, even you're gonna use these most often, and you're gonna use these least. And if I were to rank all four of them in order, it's gonna be this one most often, the 180 most often, 360 second, the 90 will be third, and then this will be fourth. You're rarely gonna use a 270 reduction, but it's good to be aware of it, because you might get a question trying to trick you that requires it. Okay, moving on to question 3. All right, this might need to be a different video still. We'll see. Yeah, I think I'm gonna end it here and then give you a separate video for question 3.